Okay, good morning. I guess you cannot imagine how happy I am for finally being here. I have taken quite a long time and a long ordeal to actually make it, but now that I'm here, I hope I'll manage to give my best and teach a little bit of scattering theory and get you started in this topic. Because I wasn't here Monday and Tuesday, do forgive me if sometimes it seems a little disconnected. Of course, we have organized the material, but there may have been things that have already been said, or there may have been things that I think have been said and haven't. So please feel free to interrupt me at any given time if there's something that doesn't make sense, or if there's something that you've just seen before and you spent an hour yesterday on. You should stop me and get me corrected. The other thing is, I've heard a little bit about the excitement and so on. I kind of like it when you interrupt me in my lectures if it's to do with clarifying points. If it's to do with more advanced topics, I prefer that you do it in the breaks. Some of you have different levels, and so you may be wanting to discuss something that goes beyond what I'm discussing here. So just for the sake of clarity, if it's more advanced, let's discuss it in the breaks. If it's to clarify what I'm saying, do interrupt me. I'll be very happy with that. Okay, so there will be homeworks today on these topics, and those Jeff is taking care of putting them on the web. And the theme will be elastic scattering, which is basically what I'll be discussing this morning. Okay, so I think we can get started. And we'll start by something that you already know, because I think that's the best way to start on grounds that you already know. In your undergraduate studies, you talked about lab and center of mass, and you talked about what the Schrödinger equation looked like in the center of mass versus the lab. And so that's the first thing that is useful to do when we solve a problem in quantum mechanics in general, and in particular in scattering. So the laboratory equation has more information than what we need. So we remove the center of mass motion. Essentially, our problem gets split into a center of mass motion part that is not so interesting, that is trivial, and then another part that's the relative motion, which is the part that matters for us. So we'll be focusing always on the center of mass relative motion and leave the other, which has a trivial solution that we know already. Okay? The other thing that's important to define right from the start is this concept of a cross-section. And actually, why don't I go back and ask you? So some of you may have already worked with cross-sections. Can you give me a sense of what the cross-section should depend on? Good morning. I'm the one that should be sleepy here. So what should it depend on? The size or the density? Only if your beam were bigger too, right? Okay.
The number of scattering nucleons that are described.
The number of scattering nuclei per square centimeter, or whatever unit that you choose. So that's one thing, is density. What else? Okay, let's go back. Let's go back and let's think. You're doing an experiment. You're measuring particles. Okay, so you put a detector. Let's say this is the target, our very original target. I've got a beam. It comes in. I've got a detector in my backpack. So how many particles do I measure here? What does it depend on? I'm guessing you didn't cover this in the last 2 days. So what does it depend on? How many particles I measure here at my backpack? So we said the density of this, and I agree, okay? So it depends on how many particles, how many scattering centers, as you named it, do we have here? But what else does it depend on? Is that the only thing that determines how many particles I measure in the detector? The solid angle of my detector. So you see where the area comes, Luke? It comes in how big the detector is. What else? How my beam. My beam might be less intense or more intense. Anything else? The probability of actually scattering. And that's what relates to the cross-section. So there's a quantity that doesn't really depend on the specifics of target, beam, detector, and that we call a cross-section. Okay? So that's what I'm trying to introduce. It's that concept. So the number of particles we get per time in the detector will depend on a bunch of things. This has to do with the flux of incoming particles. Then n is the number of scattering centers. That has to do with the density of the target. The solid angle of the detector that you very well identified, and then something else that has to do with the probability of actually occurring a reaction. And that something else has units of area and is called a cross-section. Okay? So it's this concept that there's something else that determines how many particles I get in my detector, and that is a cross-section. Now, of course, you can rewrite this as cross-section is equal to a ratio of a bunch of things, and it will depend on all these quantities in principle. But we're going to make it simpler. Okay? So just a reminder here is that the flux can be written in quantum mechanics as velocity times the square of the wave function, as you probably still remember. And so we'll use that at a later stage. Now, let me just comment here on the units. Typically, we use units of Barnes that correspond to 10 femtometers times 10 femtometers. We're a little odd. That's the units that we use. And so keep in mind that in stable beam experiments, Barnes and hundreds of Barnes and thousands of Barnes are common. But in experiments like the ones that are done in Ganil with exotic beams, you may have millibarns, you may have microbarns, you may have things that are much smaller. Okay, so now I want to simplify the expression over here and get rid of this n and get rid of this delta omega. So if I now consider something that is just out of one scattering center and measure the scattered angular flux as j hat, the final flux that is scattered, then sigma is just the ratio between the final flux scattered over initial flux. And this is a very convenient definition because now we've just got things defined in terms of in and out fluxes. So that's how we're going to define it, and if you look at it carefully, you'll see it's got the right units. Now, comment about the center of mass to laboratory. Total cross-sections are the same. It shouldn't matter whether you work in the center of mass or laboratory. But if you're looking at angular distribution, of course the angles change when you change from the center of mass to laboratory. And so if you're an experimentalist, you know this very well because you have to do this conversion all the time. Theorists usually work in center of mass all the time and sometimes forget these things, but this is it has to be kept in mind. You have to do that transformation carefully. Okay. So the picture for scattering that I want you to have in your heads for now is this picture of incoming wave, that is your beam, and we're going to consider a particle at a time interacting, so we're not going to consider these sort of coherent effects in the beam. So incoming particle that is a plane wave, scattering off a center and producing a spherical outgoing wave. So that's the picture. Your incoming beam will also go out, comes in, goes out, but in addition, it produces this ripple of effects that is a spherical wave. So keeping this in mind, let's set up the problem with the various ingredients. So first, incoming beam. Now, incoming beam could be in any direction. We're going to make the choice that the z direction is going to be along the beam. That's going to simplify our problem tremendously. And so this is something that keep in mind, the fact that we align our axis with the beam. Z is the direction of the beam. The incoming beam has certain properties depending on the velocity of the incoming particle, and so you define a momentum, and that's what gives you that plane wave coming in. If you calculate the flux is just given by V times the modulus psi squared, and that's going to be just dependent on the amplitude of that incoming wave. After the scattering happens, there's a scattered wave, that is a spherical wave, and that depends on a final momentum kf. Now for elastic scattering, kf is the same as ki, but in general it might change, right? So we'll keep that in mind. But in addition, there may be something else happening. There may be, if there's an interaction, there surely will be something else happening. And so you account for that something else with this F over there, okay, that I'm not yet getting into details, but it's something else that will depend not on R, but on theta and phi in general. And so the outgoing flux, if I define the scattered wave this way, the outgoing flux would be defined like this. And so in general, when I sum the incoming and the scattered, I'd have an asymptotic wave on the other side of my target that contains both the beam and the scattered wave, and so has a form of this sort. Make sense up to here? I'm just setting the problem. I'm not solving anything yet. I'm just putting the various ingredients to this problem. Now, we're going to call this a scattering amplitude because this is where the physics is. So we know we've got an incoming beam. There's no physics, other than the trivial physics, there's nothing happening there. We know there's something that's scattered, but it's that amplitude there that tells me what the interaction is doing, how it's changing the problem. So that's where a lot of our attention is going to go to. So let's remind ourselves of this flux that I just had in the previous slide. We've got outgoing flux and incoming flux. This J hat, don't forget, is already the scattered angular flux, so it contains the angular component, the delta omega, and Ji, that just depends on the initial velocity of the particles. And so by definition, because the cross-section, if I consider number of scattering centers 1, the cross-section will just be given by the ratio of these two, and then you see that it's basically a ratio of velocities times the scattering amplitude squared. So if we're talking about elastic scattering, what is the relationship between those two? It's the same, right? It's 1. That ratio is 1. And so you end up with a cross-section that is just the mod square of the scattering amplitude. Now, in more general cases, this is not going to be 1. And so very often people define or renormalize the scattering amplitude to take into account that kinematic factor. And so you may have seen this in books, that this cross-section gets defined as the modulus square of the scattering amplitude tilde, or something that means it's been renormalized by the kinematic correction, this kinematic ratio. Okay, so up to here, are we comfortable with the cross-section as we've defined it? Because from now on, I'm just going to be using cross-sections. We're not going to discuss any more cross-sections. We're going to assume we understand what a cross-section is, and we're going to move and try to actually calculate the scattering amplitude, which is essentially what we need to get a cross-section. Okay? So let's start with the simplest possible case. Well, the simplest possible case is no interaction, of course. So if you have no interaction, then you could solve that problem. But we're going to go for the next simplest possible case, that is spherical short-range interaction. Okay? So spherical, what does it mean? Why is spherical simple? because it has certain symmetries. Like what? I think I'm hearing well, but you are speaking very quietly, aren't you? I mean, usually I can hear, but speak up. It's okay. It's just us here and the microphone, I guess, but the microphone can only hear me. I think it won't pick up what you're asking. So please, so symmetry, yes, it preserves certain symmetries. And what does that mean? You were going to help. What were you going to say?
Oh, I just said azimuthal symmetry.
Okay. It commutes with something that's important, that's going to make our life simpler. Angular momentum, thank you. So the fact that it's this spherical symmetry means we're going to preserve angular momentum. We're not going to mix different components of angular momentum. So angular momentum, doing a partial wave decomposition, which we'll come to in a little while, will make our problem simpler. It will allow us to solve for each L without worrying about the other L's. That's basically what this gives us. So we're going to solve the problem for short-range potentials, which means that the potential is zero outside a certain range that we're going to call the range of the nuclear interaction. So that means no Coulomb for now. We'll solve for positive, and it's a time-independent problem. We're going to solve as a time-independent problem and obtain a scattering amplitude. Now, for a potential, any odd potential that I have inside a range Rn, I might not have an analytic solution. And in fact, for any case of interest, you won't have an analytic solution. So you have numerical solutions. And you do this numerical integration up to that point. And then you have to somehow match in the way that you normally match in quantum mechanics. You make the derivative and the function continuous. And that allows you the matching conditions to extract the information. So as we already concluded, spherical potential brings in angular momentum and the Hamiltonian commute, and so you allow a certain symmetry. That actually means if your incident beam has spherical symmetry, you preserve that symmetry. So your problem is not going to depend on phi. And that's what you meant by azimuthal symmetry, right? Is now your scattering amplitude depends only on theta because of this. Had I chosen a different direction for the z-axis, this might have changed. Right? And you can go back and look at the equations, what happens in those cases. But we were very smart and we chose this direction for z. And so now we've got an incoming beam that has cylindrical symmetry, and you've got a problem at the end that's going to have that same symmetry. So your equation can be written in this way, where T is just the kinetic energy operator and is explicitly written there, taking into account already the angular momentum in the conventional way, which I think you have all seen. So if not, we can offline, we can go through that. Okay, I think this is a picture then. You've got some potential. Oh, sorry. The offline people are probably thinking I'm mad. You've got some potential inside the range of the interaction, and I made the solution particularly awful. I mean, it's not physical, it's just my ability to draw in PowerPoint. But you've got whatever numerical potential, you can think of something that's not even represented in analytic form, whatever numerical potential you've got inside here, you integrate your equation out up to a point, and then at that point, through matching, you match to the scattering boundary conditions. Well, that's all very nice and clear, but this equation is not yet in a form that we'd want to apply a numerical method to, and that asymptotic condition is not yet in a form that we'd want to apply the matching condition to. So we'll have to do some manipulation before we can actually do what I'm saying we're going to do. And so that something is called a partial wave expansion. And I'm assuming you're comfortable with these expansions, but if you're not, I do urge you to go through the derivations so that, if you haven't seen these before, you need to do it at least once to understand what we're talking about. So the Legendre polynomials form a complete set, and that means that I can make my wave function, expand my wave function in this way. They are eigenstates of L squared and Lz, which is very convenient because these are the symmetries of my problem. They satisfy certain orthogonality relations, which allows me to split the problem into the various partial waves without mixing them. And then there's a particular form for the expansion that's convenient. When we expand the wave function, we'll want to expand it in terms of chi. If chi is the radial solution of the problem, we'll want to expand it in terms of chi over r, because that allows the second derivative a simpler form and can be expressed in terms of the angular momentum. And so when you put that in, so if you do a partial wave expansion of the wave function, that now is only expressed in terms of r and theta, because I've already identified that the azimuthal angle is not needed for the problem. If I do it in this way, and of course you wouldn't necessarily guess these coefficients, but we have guessed them correctly because we want them to match onto certain things, which I'll point out in a minute. But you would guess the 1 over r here just because of the simplicity of the second derivative. And if you plug this now into the Schrödinger equation that we had over here and multiply on the left by conjugate of the Legendre polynomial and integrate over angles, you get the partial wave radial equation. So it's an equation for chi that is very familiar. It has a second derivative. It's got the angular momentum component, the centrifugal barrier. It's got the interaction and the energy. Okay, so if you have not done all these steps, if before, I'm assuming everybody in this room has, but if anybody here has not gone through this, you should go through this at least once. So it's a second order differential equation that we have here. So we need two boundary conditions to be able to solve it as a differential equation. And the two boundary conditions are that the wave function needs to be 0 at the origin, the way we've defined it. Otherwise, it's going to be a problem. And asymptotically, it needs to go as we know it should go, that is plane wave plus scattered wave, spherical scattered wave. Now, note that here we've already got a partial wave decomposition. Here we don't. So we still need to do this partial wave decomposition in order to then match the corresponding L's. So the next part of the exercise is to do a partial wave decomposition of this. And for that, we need to know the solution of the radial equation when there's no interaction. So note here, this part is the part with no interaction. So we need to know what does it look like when I don't have an interaction? What's the solution of the second order differential equation? And fortunately, those are known. And I'm going to introduce them very generally already, as, you know, in such a way that when I introduce Coulomb, it will be trivial to generalize to Coulomb. Okay, so I'm not going to explicitly include spherical Bessel functions here. I'm going to define them in terms of Coulomb functions with a Coulomb parameter 0. Now this, for some people, may seem confusing now, but believe me, it'll make life easier when we want to generalize to Coulomb, because then we save trouble. So the equation that we need to solve is this equation. You can rewrite the previous equation changing r to rho, just kr, and then dividing it by the mass factor, and you get this equation, which is the free equation. And if you go back to Abramovitz and Stegan, you find that solutions of the form for L equals 0 will be sines and cosines. For higher L's, it will be Bessel functions divided by r, or multiplied by r. So we know the solutions for this, but we're actually going to use solutions for this, because sooner or later we're going to have a Coulomb interaction there. And so the general solutions for this are the regular and irregular Coulomb functions, and we'll just use those with eta 0. And then we know that if we want to generalize, we just have to make eta different from 0. So there are two linearly independent solutions that can be written as FL and GL, or if I make specific combinations of these, I can write them as the Hankel functions, outgoing and incoming. So there are certain characteristics of these functions that make it interesting in certain cases. And by the end of this morning, you'll be very confused with why I choose one or the other. But hopefully things, as we go along, will make more sense. So there'll be certain situations where I'll say I want to use Hankel functions, others where I'll want to use F functions. Now, I already note that depending on the lecturer, people have different notations, okay? So there's just no way, if you want to teach consistently, it's very difficult to get all the lecturers to have the same notation. And what we agreed is that we'll just make that point of where the notation is likely to diverge so that you can make a note yourself and make sense later. So some of us will have tried to match notations. I know Antonia's made hard effort in that direction, but others might still be using materials where there's different notation. So one thing that is very common is that the incoming and outgoing Hankel functions be represented by I's and O's, and you will see that most likely in the last week, most likely, because I think Pierre uses always this notation. Okay, so properties of these functions when the Coulomb parameter is 0. Now, as I pointed out, they depend on the spherical regular and irregular Bessel functions, and they have certain known behavior at the origin, and they go asymptotically at large distances as sines and cosines, as I pointed out. So this is what I'm thinking you've already seen this. This is what you're familiar with without the Coulomb. Now, this combination, so the FLs and GLs are two independent solutions. I can match them in that way that I pointed in the slide before, in this way, and work out what the behavior should be. And at large distances, the behavior goes as e to the plus or minus I rho plus something. So this means that it really does look like an outgoing and incoming wave. And this is useful in many cases because I have a physics picture associated with this. These functions really do mean I've got something coming in and something going out. Okay, I think this is all I want to say about these functions. Now let's look at the plane wave. So I've got my initial situation is I've got a beam coming in, and this beam is a plane wave, and I can expand it just in the same way that I said I wanted to expand my wave function. Now, if you go back to your quantum mechanics 101, or whatever you call it here, introductory quantum mechanics for undergraduates, you will probably have seen an expansion like this. And this expansion is usually written in terms of Bessel functions, J's. But they're the same thing as I pointed out. I've just generalized the form, okay? So this expansion is very inspiring, but it'll be even more inspiring if you replace that f by the Hankel functions. So if you take into account the relationship between the h minus and h plus and the f's, you can replace it and write it in this form. Now, this is the first realization, and I point this out because at least my students back in Michigan aren't always aware that a plane wave contains incoming and outgoing waves in the radial equation, because it really has to account for when the wave is approaching and when the wave is leaving, right? So it is what you expect. Naively, some students will guess in a quiz that it's only the incoming part, but no, it will have both components. It has to have both components, and because there's no interaction, it has to have them with equal amplitude. So this quantity here is 1. There's nothing happening. It comes in, it goes out. It does not get modified. In our problem, so we've already said that. We've already said incoming, outgoing. In our problem, there will be an interaction. So something will happen, and I will represent that something by an S. Incoming will happen. It will interact with the target, and there'll be an outgoing. But that outgoing will be affected because of the interaction with the target. So I will represent that by an S that has a name. It'll be scattering matrix from now on. And so at large distances, I expect this wave function externally to go as this combination of incoming and outgoing waves, but with a certain amplitude in the outgoing wave due to the interaction with the target. Is it making sense up to now? So that, of course, is in partial wave decomposition, so it depends on the L that I'm looking at. In principle, well, certainly the centrifugal barrier is going to affect the solution, so the solution is going to look different, but even the interaction might look different. Might be a function of L. So let's go back to this picture that I have of what we're actually going to do when we solve an elastic scattering problem. You have a radial equation. There are two conditions, two boundary conditions that you have to impose to solve this radial equation. Second order differential equation, so there has to be two. You'll start out integrating up to a point where there's no interaction and where you know that you can do this matching. The matching is done to an incoming Hankel minus S times an outgoing Hankel, and S contains the physics, contains what's happening in this scattering process. When you do this part, you do it numerically. You have, now I've written it in such a way that you can just apply any numerical method that is good enough, a Runge-Kutta method or a Numerov method, where you relate a second order derivative with the function, and you use finite differences to calculate that second order derivative, and then develop a numerical method to solve this problem. When I teach reaction course, this is the first homework assignment actually, which I'm going to skip because it's sort of it's very useful to understand how it works, but it does you could spend easily a couple of days trying to solve this, and then we wouldn't have time to cover everything else. So what you're going to do is use a code that's already got this numerical method implemented, and so you don't have to see it, but I do advise you to think about the details of that process, because that in the end is what's going to give you a reliable solution. So you're going to get a solution, but you need to start out the integration method in some way, and the way you start it out is by those initial conditions that you know. You know that your wave function needs to go to 0 at the origin, and you have an arbitrary, because it's a second order differential equation, the integration has to start with both either initializing the first derivative or by initializing a second point. And you can choose which one you want to use, but I wrote here that you just set the wave function to 0 at the origin and the first derivative different from 0, so you can start the integration. You apply the integration up to a certain radius that is safe, that is larger than the radius of the interaction, and then you match to the corresponding partial wave asymptotic form. And as I said, the partial wave asymptotic form has some quantity S that you do not know, and that eventually is going to give you the physics. Now, this matching condition here, the fact that you don't know S means you don't really know the asymptotic, right? You don't actually know what this is. It's the numerical integration information brought to the surface that's going to give you what that S looks like. So it's a little different if you solve the bound state problem, which I think you solved yesterday. It's a little different than the bound state problem. In the bound state problem, you know your asymptotics, and you bring it in. Here, you don't know your asymptotics. The asymptotics is going to contain physics that you need to then construct the cross-section. But you integrate out and get that. So what this condition actually does for you is set a normalization. You set a normalization for the interior of your wave function, and then in addition, you get information about that S. Now, in practice, we usually don't match just the wave functions and derivatives. We use inverse logarithmic derivatives to do the matching. And this is very similar. I guess you've done this many times in quantum as undergraduates. So we use the wave function divided by its derivative at the surface and match the numerical solution with what I know to be the analytic solution in the exterior. And from this matching, if you work it out, if you've got a value for this, and you work out this as a function of S, then you get the S matrix in terms of your numerical calculated R matrix, or inverse logarithmic derivative. Up to here. So we've gone from general form of the equations to partial wave decomposition and radial equations. We've set up to a point where we can get a scattering matrix, S of L, but we still don't have a cross-section. I mean, this is still not our cross-section, so somehow we'll have to get back to that. But up to here, is it okay? Is it all easy and I can fly through it? Or should I go slower? I mean, give me some feedback, because your faces make me feel like, okay, if you're bored, I need to go faster. No? Is it okay? Okay. Okay, now, the critical step is to connect back to the cross-section. At the end, the experimentalists measure number of particles, counts in the detector. They want to know a cross-section. That's what they want to know. So I can give them a scattering matrix that looks beautiful, and that's going to do nothing for them. How many experimentalists are in the room? Okay, do you corroborate what I just said? Come on. Yes, I see a yes. Exactly. So, I need to construct a cross-section from this. So let's go to the cross-section. So obviously, when I wrote down this radial form for the wave function, when I did the partial wave decomposition and split the dependence on angle and radius in this way, this obviously has to connect to the asymptotic form that I had before as plane wave plus scattered wave, right? So this is an exercise that is part of the homework. And I could derive it here on the board. If people struggle with it, that's what I'll do tomorrow. If I see in the afternoon that people struggle with this step, then I'll do it tomorrow. But otherwise, if I see everyone is going through it and fine, that's good. Use the partial wave decomposition of e to the ikz and e to the ikr. Everything is in the slides, so in principle you should be able to do it from the slides, I think. Try to make the slides self-contained. Use that in order to get the relationship between SL and f of theta. And if you get to this, you got it. If you don't get to that, then start again. Eventually, you should get to this. And once you get to this, then you've got your cross-section. Right? So determining the scattering, the S matrix, allows you to summing over all partial waves to determine the scattering amplitude, from which you determine the cross-section. So this that I've described here is probably a couple pages of algebra. It's no big deal. It's just using the partial wave decomposition of these e to the ikz's. So hopefully this afternoon you'll have a go at this and you'll come to the scattering amplitude. So what to keep in mind? Well, what to keep in mind is that, first of all, this is a sum to infinity. Well, it wouldn't be very useful if it was to infinity. So fortunately, our problem, if you want to think about it classically, which is not very useful in some cases, but it is useful in others. If you want to think about it classically, L goes a little bit like the impact parameter. And so at some point, you're not going to get contributions from it. So you're going to get certain region of L that contributes significantly, and then it dies off. And basically adding more L's is not going to change the scattering amplitude. The scattering amplitude, the S matrix is determined at large enough distances, and I can't stress this enough. So when you do your problem today, when you solve your elastic scattering problem, you're going to have to make sure that the matching is done at large enough distances. If you do it too close, that S of L is going to depend on R, right? You're going to get something that's wrong. S of L should not depend on R. I did not put an R dependence there and should not have an R dependence there. So that R dependence is that some students obtain is a signature of an ill-solved problem. It's not solved at large enough distances. So I'm just giving warnings already to help you not waste too much time this afternoon. Okay, so I think I can move on to different variants of how we present the results of S of L. Now, I started off, I didn't actually say very much about what this interaction should look like. I just said, well, it's short range. It's spherical and it's short range. Well, let's say it's also real. Okay, let's add also that it's real. So if it's real, then, I didn't actually have this exercise here. If it's real, you can prove that this S of L has to be unitary because you have to conserve flux. So that's a sort of added optional exercise, if you want to go through that exercise, that because you have to conserve flux, the interaction is real means you don't remove flux or add flux to the problem, then your S matrix, the mod square of this S matrix has to be 1. When you have that, then you can define another quantity that is e to the I something, because it satisfies these conditions of mod square 1. So the motivation is, why not introduce a phase? Because introducing a phase really gives the picture of what is happening for the scattering in the real interaction case. What is happening, and I have a figure here, what is happening is that the interaction is either slowing down or speeding up this wave that is coming towards the target. And so, I mean, this is just very simple to show that if you have attractive potentials, it goes one way. If you have repulsive potentials, it goes the other, and you can do that exercise. But the picture of introducing a phase is exactly that. You're either pulling in the wave or pushing out the wave, depending on whether it's attractive or repulsive. So when you introduce this quantity, if you define a phase in terms of the S matrix in this way, then you can go back to the equations for the scattering amplitude and replace it in there. And if you remember, it depended on SL minus 1, so you can put the e to the 2I delta in there and work this out and prove that the scattering amplitude in terms of phase shifts is defined in this way. So it doesn't really matter whether you're calculating a phase shift or whether you're calculating the S of L. In the end, you can construct your scattering amplitude. Now, of course, if there is an imaginary term in your interaction, flux is not going to be conserved. The S of L is not unitary. And so that delta defined in that way is now a complex object. So it doesn't have quite the same intuitive picture that I just described. But for the sake of real potential, it's actually very useful, because then you can rewrite your asymptotic form that I wrote in terms of H minus minus SH plus, if you remember, in terms of incoming and outgoing Hankel functions. I can rewrite it now in terms of sines and cosines with a phase. So it's a very convenient way of representing, because literally pulling out a general phase, you can write the wave function as a sine of something, of kr plus a delta. So it really is this picture of the wave being either shifted in or shifted out. Is this okay? So we've got S of L and we've got phase shifts. Two things to remember. It's equivalent whether I write the scattering amplitude in terms of one or the other. Now, because every single reaction theorist that came up wanted a different notation, there are more. So S of L and delta of L are two, but there's a whole bunch of other ways of representing your scattering. And so I'm going to go through it, because depending on the situations, you will want to use one or the other. And so, as I pointed out, for real potentials, phase shifts are just the easiest way of representing your problem. As soon as you put in an imaginary, it's not as useful because you don't have that conservation of flux. You don't have the unitarity of the S matrix. Another quantity that is very useful, and we'll come to it probably tomorrow or the day after, is the T matrix. Now, the T matrix is defined such that now the external part is the solution that you would have if you had no interaction. So if you remember, I don't know if you remember, and I don't know if I want to go back all that way, but the e to the ikz, the incoming plane wave that we have, if you do a partial wave decomposition, that partial wave decomposition depends on spherical Bessel functions J of L, or, in my notation, FL of 0. So if there's no interaction, that's what you get. If there's interaction, you get something else. That's the T matrix. The T matrix is the coefficient in front of the something else that you get in addition to that plane wave. So it's, if there's no interaction, you know that has to be 0. If there is an interaction that is different from 0, and it will be whatever, if you now work out the relationship with the asymptotics that I keep on. Yeah, Marek promised that I would have a board, so as I just put my chi external of R written in terms of HL minus SLH plus, right? So if you now use this relationship and compare to this relationship, you will work out this relationship. So you can obtain, again, equivalently, scattering S matrices, T matrices, or phase shifts. So we've got 3 of the lot. With this in mind, and because if you now, of course, you're memorizing all these equations as I'm writing them, right? So naturally, you've got them all present. We had a sum over L of something SL minus 1. So the scattering amplitude that I just had some coefficient here, and then it had a sum of SL minus 1. Remember? You replace the SL by that, and then you get immediately a relationship with the scattering amplitude as a function of the T matrix. So it doesn't really matter whether you choose a T matrix, an S matrix, or phase shift, but depending on the problem, you might prefer to choose one or the other just because of the physics you want to make transparent in the formalism. I think that's the best way of putting it. So a very simple equation. I bet this one you can memorize. Very simple equation for the scattering amplitude in terms of the T matrix. Now there's more. Unfortunately, there's also a K matrix, and of course there's the R matrix that is the ratio, the inverse logarithmic derivative. So in this table, it's just a summary of everything. We're not actually going to use the K matrix, so you can just delete that column. I don't think any of us are using it. Ed, am I right? Do you guys ever use the K matrix? Okay. So I think we're not going to use it in this course. Just for completeness, we put it in. But it gives you the relationship between them, and most importantly, it gives you what they should be in specific situations. So let's go back and make sure we make sense of this. So if there's no interaction, some of you have already seen it, but if there's no interaction, what did I say the S matrix needs to be? I cannot hear. I mean, my ears have gone. I don't know what's wrong with my ears.
Without no interaction, S matrix doesn't depend on theta.
The S of L should not depend on theta, regardless. So that's an important thing. Our S matrix, if we're solving our problem correctly, it will not depend on theta. The theta dependence is all in the Legendre polynomials. What else? So this is a true statement. It does not depend on theta. But what else? What is the S matrix if the interaction is not there?
It's 1.
Good. 1y, because that's a plane wave, right? And to be a plane wave, SL has to be 1. That's a representation of the plane wave incoming in, outgoing out, and same amplitude. It does not change that amplitude at all. So for zero interaction S matrix is 1, what is the phase shift? 0. It cannot shift. It has to be the same. What is the T matrix for no interaction? 0. Okay, good. So the 3 quantities are well defined for no interaction. We know what they should be. That is a check that you can do every time you solve a problem. Okay? If you don't get this, then you've set the problem wrong. For no interaction, this is what you need to get. No phase shift, no T matrix, and S1. Okay, now interaction real. What is the property of the S matrix? What do we know about the S matrix that I told you actually we didn't demonstrate, we didn't prove? It's unitary, so mod square 1. What is the phase shift? Real. And the T matrix, well, T matrix is what it is. It is what it is. It's not so simple. But this actually gives you a little handle on when you know you've solved the problem wrong. Okay, it just gives you a way to check what you're doing. Okay, now cross-sections. And integrated cross-sections are probably the first thing you do, and then you'd look at the angular distributions. I mean, an integrated cross-section is obviously, because it's integrated, it doesn't have the same level of detail, but it does give you a handle on the overall picture. So let's see what actually it does for me. So first of all, we can derive the expression for the cross-section, the total elastic cross-section, just based on the, I had it here in the corner actually, just based on the scattering amplitude. So we had this, we knew that the scattering amplitude was a sum over L, and we know the cross-section is just the mod square of this. Am I right? Is the cross-section just the mod square of this? Am I missing something? Is the cross-section just the mod square of the scattering amplitude? Sorry? Elastic is. Good. So in the elastic, I don't have kinematic factors, so or they 1. And so we can just literally do F star F and calculate the integral over all angles. That's literally what we need to do. So do this exercise. I believe it's part of the homework for today. Getting confused with the days, I'm afraid. So do this exercise, go through the steps, calculate F star F, by multiplying through the appropriate Legendre polynomial, integrate over all angles, and I bet you will get a sum of 1 minus S mod square, or if you want to write it in terms of phase shifts, of sine square of delta L. So this means that if I solve that numerical equation for all the relevant L's, I just need to calculate these delta of L's and calculate the cross-section for a given scattering energy. Right? Now, there's a very important theorem called the optical theorem that allows us to relate the total elastic cross-section with a zero angle amplitude, scattering amplitude. And note just the following. It's really simple to work out, because all Legendre polynomials have this property for when the cosine theta is 1. So they're 1. And so you can just literally use that property and say, well, if theta is 0, then the scattering amplitude is written this way. But the total elastic scattering was written in this way. So just by relating these and identifying that this is actually a sine square delta, you get an immediate relationship from the imaginary part of F theta with sigma elastic. So I didn't put an additional step here that is just working out the real and imaginary part of that e to the 2 I delta, but I'm sure you can do that. And come to the conclusion that the imaginary part of the zero angle scattering amplitude relates directly to the elastic scattering. So in a way, the imaginary part of the scattering amplitude is telling you the overall scale, so the total scattering that is going to happen. Okay, it is used both directions. So in other words, sometimes you don't know properties of the interaction and you want to pin them down, in particular of the absorption in the interaction, and you want to pin it down, and you use this relationship because you've got data on total elastic scattering. Or vice versa, if you know from microscopic theories what this should be, then perhaps it instructs what the total elastic scattering needs to be. Okay, now this is a good place. Let me check the time. I don't know how we're doing with time. We can still go a little bit more. I think coffee is 10:30, so we've got another half an hour. Okay, this is the point where I need to know, because you discussed resonances yesterday. Did you discuss resonances? Okay. Breit-Wigner forms, virtual states. Okay. So I'll quickly go through this. So yesterday you discussed this idea of a resonance being rather different than a bound state, but in a way similar, because the particles are trapped in some way, and there's just a lifetime associated with actually tunneling through some barrier. Okay, and this can be related to a phase shift. So actually, you're going to tell me what you learned yesterday. Why don't you do it this way?
Monday, so they may have forgotten.
Oh, Monday. Oh, so how do you characterize a resonance? This is always the way to get discussion going. What is a resonance? How do you know there's a resonance in your potential? Let's say you do everything I told you to do. You solve the second order differential equation numerically, you do the matching, you get a phase shift, you get an S matrix, you get everything, you get a T matrix even, and you get a cross section. How do you know if there's a resonance? Uh-oh. A peak. Where? Okay, so you solve the problem that I described for many energies, and you get a peak in energy. Good. So that's one way. So that's one idea, is to, I don't want to repeat what you went through, but there are some things I want you to get. So one way is to look at cross-section as a function of energy, and it's coming here, and then something like that. Does that work? Is that the picture that you have in mind? Okay. My drawing is probably not the best. What else is a resonance? Is anything else? Is that the only thing? What is that a manifestation of? In terms of what we've been discussing today. Why is there a peak in the cross-section? The phase shift changes. So, any particular way that it changes? It crosses 90 degrees. So, let's go back to that equation that we had. So, there's a peak in the cross-section. We know what the cross-section looks like, right? So, now you should be able to tell me, when do you get a peak? Right? I mean, now we've got a phase shift for each energy. Remember, your phase shift does not depend on R, does not depend on theta. If you've solved your problem correctly, the phase shift depends on energy. For each given energy and for each given L that you've solved an equation for, you will get a phase shift. So you can construct a phase shift as a function of energy. And when do you get a peak? When the sign is maximum, right? That's when you get a peak. So that's the magic 90 degrees. That's where it comes from. Okay, so phase shift goes through 90 degrees. What about the S matrix? It's a pole. Good. So we've got different ways of defining resonances, and these different ways aren't always equivalent, and they depend on how complex the problem is. In the single channel real case, everything is simple and transparent and clear, and all these are equivalent. And then in the real world, that is not the single channel case, everything can be much more intricate, and different formalisms may give you different answers. So this is the point I was trying to make here, and I might not have to go through all the details. So there is usually a background in addition to the resonant part. So this phase shift that we're talking about is not just the phase shift associated with that particular channel that you're interested in, but may have some other background phase shift associated with something else that's not happening at that particular energy, but is affecting that. And if you use this parameterization for the resonant part, then you get the so-called Breit-Wigner form, and that is what the experimentalists always use to parameterize their peaks and cross-sections, right? Is getting two parameters from this parameterization, gamma and ER, and that gamma and that ER actually have a very specific meaning in terms of the poles of the S matrix as people defined here. So I don't think we need to go through this in a lot of detail if you've seen this on Monday and you've discussed some of this on Monday. But the important thing that I wanted to stress is this thing. Because I want to make sure that we're not fooled by peaks and cross-sections being the only signature of resonances in your problem. Okay? So this picture, what it shows are phase shifts as a function of energy, where there's different background deltas. So if you have some other process that is occurring in your system beyond the single channel case that you're solving, then you may have a background. If you have no background, let's start with no background. If you have no background, then the phase shift goes through a resonance by rising very rapidly, going through 90 degrees. And that reflects through a sine function, sine square, that reflects as a Breit-Wigner form that is very familiar to all the experimentalists. As soon as you have anything else happening in your system that can produce a background shift, then you get odd forms. So depending on your background phase shift, you can get little squiggles, dips, you can get many different forms. And so the message that I want you to have is, if you look at cross-section as a function of energy, peaks are not the only signature of resonance, and sometimes they're not a signature. You can have the opposite. So it's only in the simple cases that you have that transparent connection, and as soon as you put in additional complexity in your problem, you can get other forms as representation of the peaks. Okay? I don't do... okay, so let's just... How many of you are familiar with energy and complex energy and momentum planes? Okay, so perhaps, I don't know that we need all of this, but perhaps we'll stick with the energy plane. Okay, we can represent in an energy plane all the states that we've been discussing in the last 3 days. And I know you discussed bound states. Bound states are real value energy solutions of your quantum mechanical problem. And so you'd represent them out here in the negative energy, and they're real. So they're on this axis. Let's picture the situation where you've got a well that is supporting this bound state, and now you reduce the strength of the well. What happens to the bound state? It's moving, right? It moves towards zero. And at some point, it can no longer bind, right? That state can no longer bind. And what happens is it becomes a resonance. So it becomes a pole of the S matrix in the language of some of you. And that really means that it's going to gain a width because there's going to be a probability that it decays away. And so that width is the distance from the real axis. The energy is still a characteristic of the resonance, and it will be the real part of the state, of that solution. Okay? So you'll have ER plus I gamma as the solution for the energy, as being the pole of your problem, and the energy is the real part, the width is the distance from the real axis, the imaginary part. You do have these odd cases in which there's no centrifugal barrier, no barrier at all. So what happens in those cases? This picture of a resonance being kind of a bound state that can penetrate through a barrier no longer holds if you don't have a barrier. And so these are the so-called virtual states. And in the case of a virtual state, you have solutions that look like kind of bound state, but they're not, because they've got the scattering asymptotic solutions. In terms of energy, they kind of come back to the negative axis, but in terms of momentum, they don't have the same momentum as a bound state. And so I don't know that we're going to spend a lot of time on this in scattering, and so it may not make sense for those of you that have never seen this. It may not make sense to spend time now, but if you want to dig it out, we can discuss it offline so that it is more complete, so that your knowledge is more complete. I had not planned to spend too much time on this, but I'm happy to discuss it for those of you that are fringing, because I know for some of you what I'm saying is making no sense. For others, you've seen it and then you're comfortable. Okay, yeah, and I can talk about the scattering length and so on, but I'll skip that. So I'm going to talk about adding Coulomb, because that's going to be essential for this afternoon, and I definitely want to make it through this part and well before the end of this morning. How many of you have seen Coulomb scattering in the classical way? How many of you remember seeing, let me ask this, how many of you remember seeing Coulomb scattering in the classical way? Okay, so all of you solved this problem, I'm pretty sure, in classical mechanics, okay? You may not remember, but all of you solved this problem in classical mechanics. Now, the classical solution is not always the quantum solution. And this is one of those cases. This is one of those cases where it is the same. So it's not always the same, but this is a case in which a classical solution actually is very useful in relating to the problem. And so many people will have a classical picture when talking about Coulomb scattering. So you can go back to your classical picture of Coulomb scattering, and you can go back to the old textbooks. All the old textbooks discuss Coulomb scattering. And you will probably find the relationship for the cross-section as a function of angle that peaks dramatically at zero angle. So in such a case, you've got this very old, this is a Satchler book from the 60s, so I took a very old book, but it's all very clear already then that Coulomb scattering was well understood. Then, of course, you look at proton-on-proton data, and you see something that deviates significantly from that picture, and so you know that something else is going on. And the something else is going on regardless of whether it's proton-proton on nickel on alphas on nickel, or anything. You know, there's going to be strong deviations from this pure picture of Coulomb scattering, which is induced by a number of things. There's finite range of the target, first concept, right? You don't have the Coulomb interaction is not the 1 over r. At short distances is more complicated than that. You all know that it goes as r squared, right? So you have a finite range effect. Then in addition to that, you've got a nuclear interaction. So as soon as the particles come close, there's going to be some deviation. At what angles will it always win? So the effects that I'm talking about are not going to be noticeable in some angles. What angles will always be Coulomb, just hardcore Coulomb? At 0 degrees. So why 0 degrees? What does 0 degrees correspond to in terms of impact parameter in this classical picture? Sorry, I couldn't hear. So what does 0 degrees scattering, what? Infinite, exactly, very far, infinite impact parameter. So at very far distances, these short range effects aren't noticeable. And so you're going to have this behavior. And if you're an experimentalist and you manage to measure 0 degrees, which of course is not feasible, but if you manage to measure the 0 degrees, you would know you have the pure Coulomb case. There will be a region around 0 that is still the case, that it's still pure Coulomb. And so that's often a way to normalize data, actually, because you know what the behavior needs to be, and so you use that to pin down the normalization if you don't have the normalization of your data. Okay, so let's now put the Coulomb inside our problem. And now it's pretty, because I set this up in this general way, putting in the Coulomb is no cost, really. It's just changing a 0 to an eta, to Sommerfeld parameter that gives us the strength of the Coulomb force. So you write down the Coulomb equation has solutions that are these Coulomb waves, FL and GL, and I'm writing them down explicitly because in one of the problems you're going to actually have to know this, I'm afraid. So that's I guess that's a problem more for theorists if the experimentalists don't want to work it out. But they defined in terms of these confluent hypergeometric functions and these interesting coefficients in front. The confluent hypergeometric functions have many different expansions that you can consider, but they're basically defined as a series. You can obviously write Hankel functions in terms of the combinations of these, just like I defined for the case where there was no charge. So it's absolutely identical. And you get, at large distances, you get this expression, but at large distances what dominates is this term. And we'll look at naturally why it's got this incoming-outgoing association. Let's see, I think I have a slide explicitly with a large distance behavior. So near the origin, the functions go as rho to the L plus 1, just like you had before. So you've got the same sort of condition, boundary condition at 0 that you had before, with, of course, additional coefficients that depend on energy. Now notice the eta depends on energy, so it's going to affect your solution. The transition from the power law to an oscillatory behavior actually happens at what is called a turning point, and the turning point, I think you've discussed that in your classical mechanics in undergraduates. It's with the energy and the potential match. So you can work out what that actually is, what's the value of that turning point, and where you get this function transforming into an oscillatory behavior. At large distances, these functions FL and GL goes as sines and cosines of some quantity, but this quantity now is not just KR plus a phase shift, it's actually depending on a Coulomb phase shift. This sigma L of eta is a Coulomb phase shift, and some other term that depends on energy and depends on R. So rho, remember, is kappa R. So now you don't get a fixed phase shift. So this is important because it means if you're actually going to use the methods that we described just a while ago and extract a phase shift for this interaction, you will actually get a pathology in your problem, because you will never be far enough to get a phase shift that does not depend on the radius because of that log term. Okay? You'll always get it. So that's why you can't use those methods. You can't match to the spherical Bessel function and hope to get an accurate solution, because you have that term there. So the solution really is to match to these functions. You need to include the Coulomb in the asymptotic behavior in order to get a stable solution, in order to get an accurate solution. Okay? So in all the matching procedure that we described, we need to upgrade our matching conditions such that we include Coulomb in those asymptotics, because otherwise we would not be able to solve the problem with the numerical methods that we've devised. Okay, so the Coulomb scattering problem can be solved exactly. So if you just have a Coulomb in your problem, we know the solutions. They're not nice. They're the ones that I just discussed. They're not simple analytic functions, but we know them. And so they have an analytic solution that we can use. And they actually given in this way, now written already explicitly in terms of K and R vectors. We can generalize and do a partial wave expansion like we did before and try and work out the same steps that we did before. So one could approach the problem and say, okay, I know that this has this general solution. I also know that I kind of like using partial wave decomposition, so I'm going to write this wave function as a sum of many partial waves, and I'm going to try and make the connection between these two formalisms. You know asymptotically, because of the properties of these functions that I just discussed, that you're going to have e to the I kz now transforming to e to the I kz plus eta log of this other function, right? So let's go back, because perhaps you forgot that. So remember that our incoming wave would be expressed as a combination of these two, and outgoing wave would be a combination of these two, and so we'd use that Hankel functions, h minus and h plus, that depend on e to the minus I kr plus something that depends on L, plus something that is specific to Coulomb phase, plus eta log of 2k rho, right? So you'll get something over here that will have that eta times log dependence, and over there that has that eta times log dependence. The difference, the reason why that's an r minus z and that's just k times r minus z and that's kr is just because there you have kz instead of kr, right? So when you replace it, you have to take that difference into account. So in the end, you can use this. You've generalized the asymptotic condition to take into account the fact that at large distances there is an additional dependence on radius in this phase of it's the long range of the Coulomb that is causing this. And you can try to do the matching in the way that we did before. But it turns out that in this particular problem, do I have that? The theory does not converge. Okay? So if you actually try to work out the problem this way, you do not get a converged result. So what you need to do is, let's not use, this can be always written formally, but it's formal because that you need to go to infinity in order to get it. That's basically why I say formally it can be written, but in practice it's not very useful. So what you need to do is more a matching where you go over this partial wave decomposition. Okay? So you can avoid the partial wave decomposition and still get what is the Coulomb phase, and that's a homework for the theorists and the experimentalists at which to work it out. Okay? That is to actually work out what is the Coulomb scattering amplitude for the Coulomb interaction, taking into account what I've just said of the long-range behavior of these functions. So when you do this matching, you have to take that into account. Okay. So I've put already, I think I've put 2 homeworks, 3. They're not all for, so these, I'm referring to homeworks, but they're not all for today. So today's, I believe, is the scattering amplitude, deriving the scattering amplitude in the total cross-section, and then that will come in tomorrow, I believe, if I'm not confused with my own homeworks. Okay, so once you get that, then it's really a trivial step to get the cross-section that is referred to as the Rutherford cross-section and that has the behavior that you derived classically before. So you get the sine force, 1 over sine force of theta over 2, and this dependence makes it peak very severely at 0 angle. That is a signature of the Coulomb. For convenience, because our cross-section is going to peak at 0 angles, and we want to see the details of the interference with the nuclear, and we wouldn't be able to see that in this log plot if we were going to plot this as a function of absolute cross-section. We will often plot the cross-section as a ratio to Rutherford. So that's actually the default of the code that we're going to be using, is to plot scattering, elastic scattering, as a ratio to the Rutherford cross-section, which means that at 0 degrees it needs to go to 1. Right? If it doesn't, then something is severely wrong with what you're doing, but it needs to go to 1 at 0 degrees. And then something else will happen. So back to the generalized scattering problem where now Coulomb is in, we have the same ideas. So essentially I've just updated the same slide, putting in Coulomb. So you've solved, you integrate numerically out a second-order differential equation with initial conditions of the wave function being 0 at the origin and the derivative not being 0. So you get the integration started. Your interaction contains a Coulomb as well as a nuclear interaction. You integrate that out to a place where it is safe to ignore the nuclear part. We have learned it is never safe to ignore the Coulomb. Okay? So we cannot ignore the Coulomb, but it is safe to ignore the nuclear part. At that point, you can match to the asymptotic boundary conditions that contain the Coulomb. They have to contain the Coulomb. And so now I have eta everywhere. So these Hankel functions depend on the Sommerfeld parameter, on the strength of the Coulomb force. And I have a S that I've put an N there because it's the nuclear effect on top of the Coulomb, right? I've already included the Coulomb in the asymptotics, but there's an additional effect on top of that, and so I'm going to put that as S of N on top of the Coulomb. When you solve this, you get this S, by matching the matching conditions, matching inverse logarithmic derivatives, you get an S. And then you construct, so I've already said this, and then you construct from that all the observables that you want to construct, or all the other quantities that may be useful to describe your problem. So in particular, if you like phase shifts, you can extract a nuclear phase shift by defining the e to the 2i delta associated with this S. And when you do that, you can also rewrite that form in the same way that we did before, but now remember all these F's and G's are true Coulomb functions, whereas before they were just Bessel functions. Now the phase shift, the total phase shift for the problem, is not just the nuclear phase shift, right? You have to remember there's also a Coulomb phase shift in your problem, and so you're going to have both the Coulomb phase shift and the nuclear added on to this Coulomb. So if you define this generalized phase shift, I think I'm going to go through a few steps to make a point. So bear with me, so I can go through these few steps so I can make this point, and hopefully it will this will be one of those things that you will keep in your brain forever. Okay, there's some things that they just don't stick. Hopefully this will stick. So you've got a Coulomb plus nuclear phase shift. You write the scattering amplitude. At this point, of course, you do remember, because, oh no, it's not on the board, but it's the scattering amplitude depends on the S of L minus 1, and if you remember correctly, that is e to the I to I delta. So that's the e to the I to I delta minus 1 that I've got there, okay? So I'm just working out what that coefficient that multiplies the Legendre polynomials and all the other little coefficients, what that looks like. Okay, I'm trying to work it out explicitly in terms of this Coulomb and nuclear contributions. So if you plug that in, if you plug the delta decomposed into pure Coulomb plus the nuclear on top of Coulomb that we worked out numerically, what do you get? Well, you can work out, you can bunch this up in such a way that you pull out something that looks like Coulomb only, and something that looks like nuclear modified by Coulomb. Okay? So let's call that this nuclear on top of the Coulomb that I already had, and let's call that just pure Coulomb. Now there's a reason why we actually split this, is because, as I pointed out, the partial wave decomposition for Coulomb only is not very useful. So we have to calculate that part separately. That part is actually done not through partial wave decomposition, it's done through what we know about the problem, because we can actually solve the problem. So we can just plug it in, we know how to calculate that, we plug it in, and then what we actually calculate numerically is the nuclear effect on top of that Coulomb. But once we have a total scattering amplitude that contains both components, and we calculate a cross-section, so actually I wrote this here explicitly. This is still calculated as a sum of over the partial waves, and when you use this form, you end up with having this correction in your scattering amplitude. So by taking into account Coulomb is not only doing the matching of the scattering, the S matrix, correctly, where the Hankel functions are calculated with the Coulomb, but it's also putting in that additional factor, which is going to make a difference in many cases. And the thing to retain that I'm trying to get the point across is when you calculate cross-sections, you do the mod square of this, and the mod square of this is not going to be the mod square of that plus the mod square of that. Okay, so the idea that you can split the Coulomb and the nuclear problem is a wrong idea. These things talk to each other throughout the scattering process. You have this difficulty, this technical difficulty of an infinite range potential that makes life a little complicated, and so the approaches that we use for the nuclear part are rather different than the ones we have to use for this Coulomb only, but you still have to consider the interference between these two effects. Make sense? Okay, so I don't want to go there now, so this is a point to stop. So I think it's time for coffee, and if it's not, I hope it comes up very soon, because my audience is sort of starting to get into the mode of my voice. Probably my voice is not modulated enough. And then we'll come back to discuss something you're going to need for this afternoon, the optical potentials. So we haven't actually talked about the interaction that exists with a target, and that's what we're going to be talking about next. Okay?